database.
Thank you. I do. I need everything.
Worry about 5 of those.
You're awesome. Thank you so much. Okay, I had to get plugged in. There we go. I'll show you my team. They're all here. They're just in the room.
Hi, team, Amy's team. I may have talked to a couple of you. Nice seeing you all. Thank you so much.
Hi all, and if you're joining us virtually on the webinar, welcome in. As we're getting started, we'd love to know a little bit more about who all is with us today. If you can drop a little bit of info in the chat, we'd love to make the most of our time. You can tell us about your role, your grade level of focus, the district that you're representing, or school if you're joining with our Oklahoma City Public Schools group. We just want to make sure that we're making the most of our time and have just that context to help customize our conversation today. And we'll get started in just a second. I'm going to give just a moment for everybody to sort of shuffle in that's planning on joining us today. And we'll get started with some introductions on our end as well. So to launch us this morning, my name is Hope Thompson. I'm the Senior Manager of Curriculum and Instruction at NextWave. I oversee all of our curricular offerings across our catalog as well as our active programs across the country. I'm a former educator myself. I'm out of the classroom. I was an elementary science teacher in Baltimore City Public Schools and in Chicago Public Schools. And I've also held roles in curriculum and instruction for robotics for students pre-K through 12. I'd love to mention that because there's a place for all of our students in STEM, and there's a place for STEM in all of our students' lives, even our pre-K students. So as we are imagining and discussing different STEM programs today, I'd just like to have us keep in mind that we are designing programs that meet the needs of all of our learners, including our pre-K students, all the diverse needs across our different student populations.
Hi, everybody. Thanks once again for joining the call. I have been working with Oklahoma City Public Schools right now for a little over a year. I may have met a couple of you that are on Amy's team. So thank you once again. I'm going to put my email information, and you can always reach out to me for any questions regarding the curriculum or equipment, anything. And I just want to say, thank you to Amy for joining us, because I've appreciated working with Amy the last year and a half, and I'm hoping this partnership will continue for the next school year. Thank you so much.
And we're also joined by Amy Fullbright.
Oh my gosh, you gave me a slide.
Sure did.
Oh, that's funny. Okay, I'm Amy Fullbright. I'm the STEM coordinator for Oklahoma City Public Schools, and I have my elementary teachers here with me. And I've been in education for 20 plus years. When I left the classroom and I left advocating for students, I said, I want to advocate for teachers. And so I'm getting to do that. So that's where I'm at.
Thanks so much for joining us, Amy.
Mm-hmm.
As we're getting started today, I'd love to know where you all currently stand with your approach to STEM. I know, Amy, you're representing a lot of different teachers in the room today, but especially those of you who are joining separately for our webinar who are representing their school or their district. I'd love to know just sort of where we're starting from a scale of 1 to 4, 1 being we'd like to integrate STEM. Maybe we've launched this as a priority, a campaign in our district. 2, we've started some initiatives, maybe a project, a PBL focused time, a STEM night with families, an after school club. 3, we have a resource, maybe we have even a curriculum, but we're looking at building buy-in across the school, across the district. Or 4, if you have a year-round successful in-school program, all your grade levels are getting STEM instruction, but you just like to learn more about the landscape, what's available, what best practices in STEM design might be. If you could just drop a number in the chat of roughly where you'd say your school, your district, or if you're representing a classroom, where you'd be on this scale. All right, already seeing some variety, which is great. Love to see a 4, 2s and 3s, wonderful. Yeah, wherever you may be across the spectrum, we're going to talk about some resources that will be helpful for you today, just to have an idea of what might be the best next steps for you, depending on where you are on that spectrum. If you are on this scale at all, you're ahead of the curve. We surveyed schools and found that 70% of the sample did not have any STEM curriculum whatsoever. And so we're relying on either individual teacher-made resources and materials or working sort of without a curriculum at all. So wherever you fall on this scale, know that we're going to have some resources and ideas to help to work you up along that scale today. To begin, a little bit of introduction of NextWave STEM. We believe that the world needs young innovators, so we offer hands-on courses in emerging tech. So our goal is to make sure that students are not just consuming or using these technologies, but they are getting to build the tools and skills to use them to design and to create, expressing their own creativity, creating a culture of academic risk and learning to fail without fear. Our goal is always to empower teachers of today to prepare students for what we have long called the careers of tomorrow, the technologies of tomorrow, but what are increasingly the technologies of today. These are tools that students already live, work, and learn among, and we want to give the students that we serve the tools to use them, the skills to use them effectively and safely in their lives and in their work. To get started, I'd love to know, especially if you're not at a 4 yet, what sort of barriers prevent schools and districts from implementing STEM programs? What kind of challenges come up for you as a classroom teacher, as a school administrator, as a district curriculum leader? What barriers have prevented you from getting to 4 yet? Or if you've recently gotten to 4, what were some of the barriers that you've navigated along the way? If you could just drop a word or two in the chat about what has kept you from a STEM program that is long-term and sustainable in the past. Yeah, so big ones that we hear, are the time, the funding and the budget, how those resources are going to be procured, the teachers, whether that is a concern around staffing, around background knowledge, around training, how we're going to make sure that the teachers that are implementing have the buy-in. What kind of standards are we looking at when we think about STEM? It's a really broad topic, so how can we be specific about what those learning objectives are going to look like? All right, we're going to talk about all of these. Fortunately or unfortunately, we do hear about the same big barriers from a lot of different schools. So while it is, an unfortunate reality that a lot of schools and districts are facing the same barriers, it also means that we're really able to target those challenges when we're designing solutions. And the big ones that we hear, staffing. Who is going to be providing this instruction? If it is existing educators that are already part of our school systems, how do we make sure that they have the background knowledge that they need, especially at the older grade levels, middle and high school, when we're deepening that complexity of the tech and we're thinking about emerging technologies that are really rapidly evolving in real time? How do we make sure that the quality of instruction is backed up by the content knowledge? As well as what curriculum we're using, what standards are we aligning to in the first place, and how do we make sure that this curriculum is easily replicable and can be presented with high fidelity across our school or across our district? And then the big one being, of course, resources. Where is the funding coming from for these technologies, for this curriculum? Or is this something that we can use with resources we already have? We had a grant that got us 3D printers in 2015. Can we pursue some solutions that are related directly to that? Or those robots that have been in the closet since that teacher who loved STEM moved on? How do we make the most of resources that we already have? We're going to address all of these, and because they are not something that only one school or district has encountered, they're pretty well-trod territory. And it's part of what NextWave STEM does to address some of these concerns, because we know these challenges will come up along the way. And we're also going to be really specific about what we mean by STEM. When we talk about science, technology, engineering, and math, that can be such a big bucket that it becomes this nebulous concept, and it can make it harder to actually meet goals for having STEM integration in the classroom. If you should always be doing STEM, but you're not really sure what that means, it can be hard to measure for our students and for our teachers the success of a STEM program. So we're going to focus on 3 major pillars of STEM when we talk about that particular acronym today. One being the practices and process of science and engineering. So having students build the skills and practice of the engineering design process of asking a question, identifying problems and solutions, planning them, testing them, and engaging in the iterative process of testing and improving, repeating that over and over again until the goal is met or the solution meets the required criteria. Another pillar is the technology in and of itself. What sort of innovation has happened when experts engage in that engineering and design process? And that's valuable because students get to see the outcome of that engineering design process. They get to engage with technology that's already in the world that they live and learn in. And also there is inherent value in building buy-in and engagement with students. There's an inherent excitement from putting drones in the air, working with robotics, seeing a 3D printer, and we can use that to our and to students' advantage in building engagement with these concepts so that we can really rely on that third pillar as well, which are the discrete skills, the measurable learning outcomes, especially as they relate to coding, programming, computer science, that students are building. And working in tandem with all 3 of these, ideally any given STEM program is going to address at least 2 at one time, but ideally all 3. Students can build a more holistic approach to their STEM learning, and schools can build more holistic STEM programs that give students practice in the process, the outcome, and the skills throughout the courses. And we see schools do this in 2 major ways. There's 2 sort of pathways towards effective long-term STEM programming. One of them being standalone STEM instruction, and the other integrating STEM into core subjects throughout the school day. We're going to talk about both of these, and we're going to start with standalone STEM instruction. And this can look a variety of different ways, as I'm sure many of you can imagine, either after school and in out of school time, robotics clubs, STEM clubs. Saturday, we've also seen some Saturday out of school programs, a PBL day, or in the school day. We see standalone STEM instruction happen in many fortunate districts. They're able to protect STEM time, even if it's 25 minutes. That's a protected part of the school day. We also see it as special alongside art and music, a STEM rotation, or having it be part of the library and media science curriculum. Those are all different opportunities for protecting that STEM time so that it is dedicated not as part of science or math, but as its own subject. And when we do that, we want to think specifically around the standards we use. I saw this come up in the chat earlier, to design STEM curricula and STEM programming around something measurable for students. And we're going to focus on the computer science standards. Oklahoma has really robust computer science standards, some of the most specific and detailed in the country. They are inspired by and developed from the Computer Science Teachers Association standards, but are actually more specific than those even, because they go grade level by grade level as opposed to a grade band. And these provide a great framework for us to make sure we can measure some of those skills, that third pillar we talked about, with students throughout a program. And they fall more or less into these 5 buckets. Computing systems, understanding the hardware, software, the relationship of input and output with these technologies, as well as the practice and ability to troubleshoot around the use or misuse of computing systems. Networks and the internet, understanding the transmission of electronic data and basic concepts of cybersecurity. For our youngest students, that's just understanding the concept of password protection. For our high schoolers, those are going to be more detailed cybersecurity concepts. Data analysis, that's a huge potential tie-in for other math and science skills as well. But this is going to be a lot of the organization and presentation of data, how it's represented and interpreted, and then especially with our students in middle school and beyond, thinking more about decision-making based on that trend prediction. Algorithms and programming are going to be where we find those highly specific computer science skills, as specific as using certain kinds of commands when writing a sequence for a program, but also having the ability to test and debug a program, where we do get to see a lot of opportunity for some of those softer, harder to manage, harder to measure skills like academic risk-taking. The trial and error that's really built into coding provides a lot of opportunity for practice in that. And then also making sure that all of this programming, all of these skills that are being developed are rooted in problem solving, how these technologies help to improve our worlds that we live and work in. And then impacts of computing, a little bit more of the social science, the humanities aspect brought into the conversation around technology, how we see it represented by society and ethics, what kind of conversations around bias and accessibility can we have when we're working with these technologies, and an exploration of career paths. What can students do with this information and these skills that they've developed? Now, these 5 buckets extend across all K through 12, but I want to give you a bit of a picture. If this is your first time working with these kinds of standards before, what that looks like across that spectrum from your youngest learners up through middle school and high school. So with something like algorithms and programming, this single standard across those grade levels, you can see increases in complexity. And then we also see that higher order thinking represented more as our students get up into high school. So just being able to, with a little bit of guidance, debug an algorithm. With our youngest students, this may be one that the teacher has identified as not functioning, versus our 4th graders, they're going to try it out themselves, or analyze and understand what's going wrong with the program that they've written and identify those bugs. And those programs are also more complex. With our 1st graders, it may be an actually unplugged activity where you're giving instructions to a classmate to cross the room and get a red marker, and we're finding out that the instructions are not exact. Versus our 7th graders, they're working with a really complex program. It's got repetition, it has variables, it's explicitly a programming language. We're working with a software. At the high school level, we are accessing a little bit more of those higher order verbs that we're going to recognize, like evaluate and refine. Our students are having a little bit more of judgment around the success of their programs. And they're also thinking with a more specific end goal in mind, making them user-friendly, making them efficient, making them accessible. Not just are they functional, but are they meeting these higher criteria? Or at the very highest level, our 11th and 12th graders are thinking more systematically. What kind of test cases can we design to approach debugging in a more systems level lens? And the same thing goes for this impacts of computing standard that we've grabbed. We're going from identifying how people are using technologies to designing a study that evaluates or predicts how they may continue to evolve. So we are working with the same concepts, but we are deepening the complexity. We are getting higher order thinking and learning happening for our middle and high school students. And we are getting to broaden that lens a little bit into society and culture at large. So because of how specific and how detailed each of these standards are, we're going to pause our deep dive of these here today, just so that you don't have to watch me read standards all morning, but you can get an idea of how specific these can be, which as someone in the classroom, you can recognize as a really helpful structure to make sure that you're making the most of your instructional time with STEM. When we're looking at designing a program from those standards, we're going to start with this quick look at all of the NextWave STEM courses. We're not going to look at every single one of these today. We're going to focus in on just one particular pathway. But across that top row, you can see the 7 different pathways that we focus on at NextWave. robotics, drones, AI literacy, 3D tech and design, innovation, sustainability, and game design. With each of these standards in mind, we can put together a suite of courses. Anywhere between 2 and 5 of these courses will be a full year's worth of instruction, depending on how much time you have dedicated to STEM, how frequently you're seeing your students, or how frequently those classes are designed. And you can put together a different focus for each section. So something like robotics, drones, AI, they're going to have a little bit more of those algorithm and programming standards. That AI literacy course is also going to include a lot of the impacts of computing and discussion around where those technologies show up in our world. Something like 3D technology and design, game design, they're going to have a little bit more of an arts focus. Innovation, entrepreneurship, a lot of practice in the engineering design process. So we're getting that process a little bit more. And sustainability, that's going to have some connections to core science classes. They're going to get to see those technologies impacting existing industries, a little bit of those impact of technologies as well. So we're going to focus right now on just the robotics course in particular, so that we can do a deep dive of how one particular pathway can meet some of those standards and be a jumping off point for additional STEM programming. So for our youngest students, what that can look like is a really simple robot and offering a lot of practice in the concepts of coding, something like the foundational decomposition and sequencing skills that students will need later on as they have more complex softwares that they're coding with. So for our K through 2 students, they're using a really simple robot we call Colby. It is only one device, so they're not making a connection to another software. They are inputting a program by pressing the buttons right there on the robot. They're also getting a little bit of connection with other skills because they're using those commands to write programs that draw a number, that tell a story, that solve a problem. And they're getting to develop some more comfort with sequencing, so having to build out the instructions before pressing go. So I've grabbed just a couple of the standards that those are going to hit here. So just as a little bit of a snapshot, you can see some of the first grade standards that this kind of programming is going to be aligned to. Modeling daily processes and following algorithms. So with our youngest students, we don't even have to bring in the robot just yet to be practicing those skills. Anytime that they are breaking something down into steps and discussing those even verbally is an opportunity to practice those skills. Collaboratively or independently creating programs to accomplish a task. So are getting our mouse to the cheese. Can we work together in a group to write a program that makes that happen? What happens when we introduce a mousetrap here and a wall there? How we can work around some of those challenges. Breaking down those steps needed to solve the problem. Students are not going to press forward, go, turn, go. They're building out the steps. Forward, forward, turn, forward, and then pressing the run button on their device. So they're building the skill of breaking something down into smaller steps to solve the problem. And this is just a picture of a couple of standards. It extends a lot further beyond them, but again, I don't want you to have to watch me read standards all morning. For our older students, as we're looking at upper elementary, we can introduce a more complex language. So they're working with block coding, where those commands are mostly written, but students are manipulating a little bit of the data inside them and fitting them together to make a program. They're working with a robot that's also a little bit more advanced, something that they have constructed themselves. They build this MBot. And they are working to write programs that are a little bit more sophisticated than what they've been working on in K through 2. The robot may be tracking and following a line, responding to sound. It's using things like flashing lights, so the students are getting a lot of experience in working with different commands. We're also going to bring in more specific standards of what the students are actually building in these programs. They're using sequencing, certainly what they practiced in K through 2. They're also bringing in conditionals and variables. They're using if-then thinking to build out programs that are more responsive. They're using variables and some algebraic thinking to understand what kind of information those variables carry with them. And they're working independently and collaboratively in groups, but they're also coding independently to work through different kinds of algorithms for for the same problem. So we may have multiple students working on programs that achieve the same solution in different ways. At 6 through 8, our middle schoolers, we want them to be bringing all of these skills back into problem solving and real world robotics. So making those programs a little bit more responsive with or without human intervention. So can they write a program where the robots are using sensors to respond to the world around them? Whether that's responding with lights when they encounter a wall to let the user know something has gone wrong, or turning around, or responding with sound, but something that is a little bit more sophisticated. It does not require immediate intervention when an obstacle is encountered. They're also combining these skills not only to engage in these challenges, but to design challenges and competitions for their classmates to engage in. So once again, grabbed a couple of standards. They're getting a little bit more detail in the conditionals, the variables, the types of commands that they're using in the program. They're also working through some of the skills of being part of a programming team, collecting feedback, understanding how to incorporate different points of view within this team, as we do see those kinds of skills show up in careers in programming. We again want to be zooming out a little bit further so that students can see how robotics fit into different industries while they develop some of those career skills. So for our high school students, this means all these programming skills that we've built, how do we take those and put them towards a career in robotics? What does that actually look like? Our focus at the 9 through 12 level is the kind of automation that we see happening in the manufacturing industry. So we take a simple single board computer like the microbit and a variety of extensions and expansion pieces and use them to simulate the kind of processes that we see in manufacturing. So for example, this course, while it's working with the same kind of programming languages we've seen at the younger levels, we also bring in text-based language. So students are working with something a little bit closer to what the industry is going to require in terms of complexity. Working with the text-based language like Python is something that students will use upon graduation more than a block programming that was giving them the introduction. Also, students may culminate with this particular unit with a project like using the conveyor belt, the sensors, the sorting wand, and the single board computer to code a program that sorts an item independently and autonomously as it comes down the line. So they get to see the kinds of skills they've been building applied to careers that they can immediately pursue. Grabbed a couple standards here as well. They're providing solutions to a variety of users using a software development process. So they're engaging in that in engineering and design process in a digital space. They're working with the team to develop and test it, but they are thinking more systematically when it comes to debugging as opposed to case-by-case testing and waiting for an error. So this is just one particular pathway that we've seen all the way K through 12 at how we start with the foundational concepts, maybe some simple technology, and add in a little bit more complexity, whether in the depth of the skill, the type of software, the type of hardware or robot that we're working with, and how easily and directly it relates to the industry career level skills that students will need. Now, when we saw that entire course chart, you saw each of those pathways could have this exact format in different technologies and different topics. And this robotics is just one. But I want for you all to get to hear a little bit about what that dedicated STEM time can look like in a different capacity. So I am going to pass it over to Amy Fullbright to talk about NextWave STEM's dedicated STEM approach in Oklahoma City Public Schools.
Thank you, Hope. In Oklahoma City, we have standalone STEM programs. Each one of my teachers in the room, they are the STEM teacher at their elementary site. And in some cases, the STEM class is part of their specials rotation, but then in some instances, it is just a standalone schedule. So students come all of the elementary schools see 1st through 4th. Some see kinder, some see pre-K, and some see some of our special groups. So it's a lot of exposure is the name of the game in elementary, and it's unique to Oklahoma that they actually get to go to a STEM class that's dedicated, focused on that kind of learning, because it's different than classroom learning, and we're seeing that. So in the classrooms, they're focusing heavily on math and reading right now because that's the needs that our students have, and then they get to have that project-based learning experience when they come to our STEM classrooms.
Thank you so much. We just want to provide a couple of examples to help you visualize the way this could look in your classroom, your school, or your district. And we're really excited about our partnership with Oklahoma City. And like Amy said, it's great that you're able to have dedicated STEM instructors and the space to explore how this does look different from other classroom instruction, and what opportunities that provides for students when they get to be so engaged in this really student-led inquiry process through STEM. But we also know that not all schools, not all districts, not all classrooms have the option for standalone STEM instruction, and it is no less important to bring STEM to your students and your students to STEM the way that you can. And we want to help you visualize that and make that happen. So for a lot of schools that we work with, integrating STEM into core subjects is the best way to bring students to practice with the process, the technology, and the skills that we've been discussing. This can look so different across different subjects, different schools. For one school that might look like using a drones program to help practice math. There's a lot of opportunity for measurement and for the kinds of coordinate plane practice that you want your 4th and 5th graders to be getting that you can use with drones. You can be using AI to explore different concepts, even in ELA, which I know can be a scary thought, especially with ELA teachers. I was formerly an ELA teacher myself, but we can work with students to create their own chatbots where they are writing their own script for a chatbot to behave a certain way. And they're understanding things like tone. I want a playful versus a pedantic chatbot. I want to create a chatbot that behaves just like the character from my novel study to show my understanding of their characterization. So we can use these tools in unexpected ways to underscore the goals that we have in existing class time and in instructional minutes that we know are so precious. We're going to focus in on one in particular today. Again, just one standard, one technology to exemplify what this can look like with just one focus. But know that there are 1,000 different ways, and we would be more than happy to discuss other ways that you could integrate. This is just one standard for life science across K through 12. So for our students in kinder through 12th, this life science concept of what plants need and how human life and society affects those. So for our K students, just understanding what it is that plants need to survive. Our 2nd graders are planning and conducting investigations to see if they need sunlight and water. By 5th grade, our students are supporting an argument that plants chiefly require air and water. And 8th graders are working through the scientific explanation based on evidence. So we really want to be building that practice of a scientist for them in environmental and genetic factors influencing their growth. And then in 9 through 12, understanding how to construct an explanation that describes how solutions might mitigate the adverse impacts of human activity on biodiversity. So this is just one standard that we've grabbed out of the existing core subjects that we know our schools are focused on and that dedicated instructional time is devoted to. And we're going to look at how one technology introducing hydroponics can impact all of those standards and all of that instruction. So if we were looking at one school, we'll just imagine a K through 12 school to represent an entire district here. Introducing this one technology, just 2 of these shelves even, would provide some of that tech integration and STEM integration for all those grade levels. So if you haven't worked with hydroponics before, it is a shelving unit that you can see right here. It can be as small as this about 1 foot by 2 foot unit, or warehouse full for a larger operation. But in the classroom, it's this pretty inobtrusive shelf where we are growing plants with a deep water filter and UV ray light. So we have a structure for the plant to hold on to, but there is no soil. There are some nutrients that are delivered through a liquid plant food in the water filter. But other than that, it is growing without the usual soil. With this one kind of technology, we can see with just a few weeks, this is about 7 weeks later, we see all of these really abundant leafy greens grown, and we can apply this tech across different goals. So for our K through 2 students, this is a great way to enliven an existing plant life unit. I did this unit myself with the seed on a wet paper towel and a bag on the windowsill. It's a great way to get to see the process of germination, and actually has a place alongside the hydroponics unit in our course, but is a little bit more controlled. It's a little bit more consistent than the seed on a wet paper towel. It provides students with an opportunity to grow quickly more complex plants, practicing on the parts of the plant and the things that plants needs, but it also has the supported materials like additional exploration of seed dispersal and how we see plants show up on our kitchen tables and in our food. So it's a great way to have a little bit new life breathed into existing plant units, and also bring in this technology to show students what kind of innovations are happening in even disciplines we take for granted as universal and enduring as plant life. For our 3rd through 5th grade students, it provides a great arena for some of those scientific practices. So students get to have this perfect lab for designing and conducting those experiments that are part of their standard. So they can look at what plants need to grow by isolating and manipulating some variables. Students are growing using that deep water culture. They can use different combinations of plant food, water, vinegar, lemon juice, and measure the plant growth across those experiments. They're getting a lot of practice in the data collection and scientific observation practices that can be hard to measure and hard to isolate in the classroom. At our 6 to 8 level, we're able to have a little bit more complexity in the science that we're doing with these plants, things like measuring pH. They can pull leafy greens and put them under a microscope to look at chloroplasts for their understanding of photosynthesis. But they also are getting to, as we always want to be doing with STEM, especially at the middle school level, connect these technologies to problem solving. How does hydroponics and this exciting technology that developed out of the engineering design process, how does it help us solve existing problems or to improve our lives? What does hydroponics pose as a potential solution to issues like food deserts and produce availability? Students engage in a project where they have a design hydroponic system for a space flight to sustain the life of 6 astronauts as they explore this long-term space campaign. So we have to think through where these solutions or where these technologies show up as potential solutions and how they improve our lives. At the high school level, we wanted to broaden the lens into existing industries and focus on that career aspect, that CTE approach. So how does hydroponics fit into a larger scheme of what is going on in the world of agricultural science? So students are learning about things like agribusiness, they're understanding land management and pest management and irrigation systems. They're getting a more comprehensive survey of agricultural concepts. They're also getting to see the connection between the different worlds that they're learning about. So they're growing with the hydroponic system wheatgrass from seeds. Then they are blending that wheatgrass into a health drink. Then they are designing a business plan to bring that health drink to market. So they're getting to see that full scope of the interplay between all of these concepts of agriculture, the world of business, again, making that connection between what's growing and what's at our kitchen table. Now, that's just one example for how we can integrate a single technology across grade levels. It's not, of course, the only way. All of our NextWave STEM courses do have standards alignment to help guide, whether it's standalone STEM time with those Computer Science Teachers Association standards for coding, whether it's NGSS more designed for science, core science, but also ELA and math. If you need to make the most of your instructional time, we want to help you see how you can make those connections between the STEM world and the dedicated instructional time that you are already focused on and that you know your students will be getting. So if there is the potential integration into the ELA and math world, you won't have to figure that out and start from scratch yourself. We have some of those sort of delineated by our standards alignment. We also do have the 21st century skills of collaboration, communication, creativity, critical thinking, things that all teachers can agree are really important for our students to have, but can be hard to measure and hard to carve out in the school day. And as an educator myself, I understand that it all comes down to the standards alignment, the quality of that instructional time, and that curriculum that you're working from. So I really like to lead with just the fact that these underscore all that we do. The standards alignment is the first point from which we build our content. As for the other resources, when we looked at that course chart, we'll look at it again in just a moment. Every one of our courses, all the way K through 2 through 9 through 12, is a 15-lesson, 15-hour course, including course guides and foundational materials like scope and sequence documents. That's going to take you through every single objective and every single standard alignment for the lessons. Teachers' guides, lesson plans that are highly, highly supportive, especially if staffing and background knowledge is a concern, is a challenge that you've run into in the past. These are the kinds of supported lessons, I call them just sort of scripted, that if you are not particularly familiar with an evolving and emerging technology, we understand. That's our job. We stay up to date on all of these technologies and deliver them in the form of these lesson plans that require someone who is comfortable in front of students and leading students in an inquiry-based lesson plan that allows them to facilitate knowledge alongside some of the professional development resources that we provide. So if you're very comfortable with 3D printing, you can follow these as a guide, just relying a little bit on your own background knowledge as well. But if not, this is your first time working with, say, 3D printing, you can follow these to the letter, review our PD resources, and be comfortable and prepared to lead students. We also include presentations, visual guides for your students throughout the lesson, assessments in the formative and summative forms with worksheets and final tests that can be administered pre and post. And then all of this is hosted on our online teaching portal. So you have access to this the entire length of your relationship with NextWave STEM, including those videos and resources to get your teachers up to speed on these technologies. And we also provide all of our student-facing resources in both English and Spanish. So if you have a bilingual classroom, or if you want to provide additional resources for any of your learners who are Spanish speakers in the classroom, we do have that option as well to provide presentations and worksheets in Spanish. The other big challenge that we hear schools and districts up against is the funding, the resources for these programs. We want to also provide some assistance in making that happen. So we have a list of federal and commercial grant opportunities on our site. I highly encourage you to check those out if funding has been a challenge or a barrier in the past. We also have a template for applications. So that process of applying and designing an ideal application we know is a time suck on teachers and educators and administrators who already have a lot on their plate. So we do provide a template to help get you started on the kind of language that is successful for securing that kind of funding for your program. And it may also depend on what you already have in your schools or what your focus is going to be on technologies moving forward. You can see from the very bottom here, this key, some of our courses have no hardware required whatsoever if you want to get started right away, or if you're looking at a reduced amount of funding that you're working with. So something like our AI literacy or game design courses can be done without hardware, as long as students have devices. Some of our courses are hardware agnostic, so our 3D design pathway. If you already have 3D printers, you can make that happen with whatever machines you have. And others are hardware specific. So looking at our robotics pathway, you can see we have courses for MBOT, for the Bolt, the Wonder Workshop Dash, for the Vex Go, depending on what robots you may already have from that grant that you had or that really excited STEM teacher. If you've got them sitting in a closet somewhere, we really want to bring those out, dust them off, and make the most of the technology that you have in the building. If not, we do also have hardware available for purchase with us that goes along with each of these courses. So like I said, as we're looking at this one last time, this course chart, each one of these boxes, each of these titles is a 15-lesson core course. Some of them do also have supplementary lessons as the technology has evolved. So some go up to anywhere between 18 and 28 lessons. I really, really do stand behind the quality of our curriculum. I highly recommend looking at our lesson plans. They are really, really supportive and detailed. They include things like differentiation options to meet the needs of all your learners. They're really clear and they're a standards alignment. They're goals for student learning outcomes. And I think I'm really proud of them, and we at NextWave STEM are really proud of them. So we highly recommend checking them out. I really want to thank you for your time today, and I want to thank Amy so much for sharing a little bit about what NextWave has looked like at Oklahoma City Public Schools. We will stick around for a few minutes to answer any questions that you may have about NextWave, about STEM, what it can look like at your school. As an educator, nothing makes me happier than getting in the weeds and really thinking through program design and meeting the needs of your school. So please feel free to stick around, drop a question in the chat, or come off of mute and we'll chat through it. But thank you all so much for your time today. And I wish you the best in bringing STEM to your students.
Thank you so much, everyone.
Sorry. Thank you, Hope. That was wonderful. Amy, anything that you would like to add? Because I know you've been exposed to a lot of what we do, and I think you've talked to your team about what we do and how we do it. Anything that the team wants to talk about? Anything?
No, my goal is just providing resources because each school is its own ecosystem and each school is run completely different. And so if there's a need for a more tailored curriculum for what we already have, that is really my goal in today, is just saying here are some more resources for what we already have in our STEM classrooms. So
Thank you.
you're welcome.
Thanks for being a big proponent for us. Okay, thank you. And then anybody else, and I know we have people from other districts. Anna, with whom I had a meeting last week, she's on. Thank you, Anna, for attending. And she's looking at bringing our programs to her district. So I put my information in the chat. I've met with a couple of you in the past. If any of you need any additional information, please reach out to me. I'd love to set up a time to speak with you. I can bring Hope on. Whatever you need, we are a resource here, and we would love to partner with you as a STEM partner, okay, for this year and beyond.
Thank you all so much.
Thank you, everybody. Thanks, Amy, once again.
All right, please reach out if you have any questions to either Jay or I. This recording will be emailed out to you, so you can review all of the resources here as well. Thank you so much for your time and your participation today.